This problem's similar to one we did previously. What's the molar solubility of PbI2 in a 0.1 molar NaI solution? So the first thing we want to do, so it's got the Ksp, so we can recognize this then as some sort of solubility problem. So we're going to go ahead and write out the part that we know. We're going to have some sort of equilibrium having to do with our lead iodide. Now, usually when we write our rice tables, we have this initial part, and we've been having an initial where just everything is 0, and we've just moved on with the rest of our lives. Now, in this case, though, that's not actually true, because now we have 0.1 molar sodium iodide. This will, in fact, give us an initial concentration of iodide. So if you can imagine, we actually have our little beaker down here, and not only do we have this rock, this is a rock, of our lead iodide that we've thrown in here, but we've also thrown in here sodium iodide. And so as we throw in that sodium iodide, we're going to get sodium ions and we're going to get iodide ions. How many are we going to get? Well, we're going to get the same amount that we have of our initial, because everything's in a 1-to-1 ratio. So this should in fact give us a 0.01 molar concentration initially. Now we didn't give ourselves any extra lead, so our lead will still be 0. The change, this is where it's really tempting to try to make the equilibrium go backwards, but you guys will remember that anytime we have a 0 here, we've got to have positive something. We don't want to have a negative concentration in the end, so we've got to actually have a positive change so that we don't wind up with a negative lead concentration in the end. Likewise, when we're looking at iodide, then, since it's both on the product side, we already decided that one product's going to be positive, the other one's got to be positive too. So then as we do that, we do actually need to add our change to our initial. So this is now where we are at equilibrium. So then when we come down for Ksp, we can write our Ksp expression. There's our lead, our iodide, that's going to be squared. So now we can go ahead and use our expression, and now we can plug in the values that we have. So now we'll have an x for our lead, and for our iodide we're going to have 0.1 plus 2x all squared. Some of you may now be having flashbacks to when we did the quadratic equation. The really nice thing is now that we are past asking you guys about the quadratic, it can still come back on the final, but we're done with that for now. And if you'll remember, we also had those lovely times where we could assume that x is small. So that's actually what we're going to do here. We're going to assume that this x is 0. And that's something that we covered previously, so if you have questions on that, that comes from a previous unit. That has a lot to do with the fact that I'm all the way down here at 10 to the negative 8. So the change that I'm going to be experiencing is relatively small in comparison. So again, that equilibrium value is going to be pretty small. So since that goes to 0, that's all 0, and this is what I'm left with. So I do still have to square that number. I don't get away from the actual mathematical operation. I still have to square that. 0.01. And then I should just have divide everything by that. Should give me an x value of 1.4 times 10 to the negative 6. So, and then again, once I'm all done with that, I want to take a step back and make sure that I actually answered my question. So I wanted to know what the molar solubility was, and as we'll recall, once you have molar solubility, what you're really looking for is something that's going to be in a 1-to-1 ratio with your lead iodide. So the x actually is going to be our molar solubility. So our molar solubility then is our 1.4 times to the negative 6 molar is in fact our molar solubility. So the main thing that has to do with this one is, the main thing that makes it different is this is a common ion effect problem, which means that we actually had some sort of initial concentration. So there have been plenty of times when we've asked for molar solubility that we've been able to just ignore most of the rice table and just ignore our initial concentration. But when you actually have that common ion in effect, you don't get to do that. It has to go into account, shows up in your KSP expression, and it has to go through the whole rice table.